Hello all, I'm Amoga Priya from Group 15 and my group members are Kirtiga, Mansa and Rachana. So moving on to first problem, bit rate performance comparison of QPSK and 64-QAM modulation schemes over AWGN channel. I'll start off with uh, code explanation. First is the simulation parameters where code sets up simulation parameters where the number of bits determine accuracy and the SNR range lets us see how modulation scheme react to different noise levels. Next is set the model names, QPSK model and QAM64 model. And we are pre-allocating the result arrays, where arrays are created to store bit error results. So this way we can collect and compare the error performance for both QPSK and 64 QAM as SNR changes. So I have opened for running QPSK simulation, for loop is open, where inside a loop for each chosen SNR value, the code updates the AWGN channel's noise levels using workspace variable, where the Simulink then runs the selected models, either QPSK or 64 QAM, and simulates sending random bits through the system. The same thing has been done in 64 QAM simulation. When each simulation finishes, the code reads out the bit error rate from Simulink error rate calculation blocks. This shows how many bits were received incorrectly at the SNR. Then, for the plotting the results, all these bit error rate results are kept in arrays. So after each SNR is tested, the code uses this MATLAB function semilogy function to plot bit error rate against SNR for both modulation types on one single graph. I've added the theoretical curves also, where we have used an bit error rate AWGN function and non-differential encoding function. So the last step is for formatting the plot, where y limit, x label, y label, title, and legend are there for comparison. Lastly, the simulation complete command shows us the final result. Moving on to explaining Simulink models. First is QPSK model. So in QPSK model, the first block is Bernoulli binary block, where this block generates a stream of random binary data. So this simulating the source information bit sent by transmitter in a real communication system. Next is QPSK modulator block, which is where the binary data is converted into QPSK symbols. In QPSK, every four possible phase states, in QPSK, every two bits are combined and mapped to one four possible phase states. So this is boosting the bandwidth efficiency. The output of this is given to AWGN channel. So the block adds additive white Gaussian noise to QPSK modulated signal. The noise level is thus controlled by SNR parameter. Next, this output is given to QPSK demodulator block, and the received noisy signal here is converted back into binary bits by demapping the QPSK symbols. So the demodulator tries to guess the transmitted bits based on the each received symbol phase, accounting for the added noise. So this output is given to error rate calculation block. So this block compares the transmitted binary data with received bits and calculates the bit error rate. So which is the fraction of bits that were received incorrectly. Next, the block is the display block, which is shows the display or output is shown here, and followed by that output BER data to workspace block is provided, which provides the process results such as BER values. So the moving on to next QPSK model, moving on to next simulation model, which is QAM64. So even here, I've used the Bernoulli generator block, same as the QPSK, and this is going to 64 QAM modulator baseband, where the parameters have given us 64 MRA bit type, and again this is going to AWGN channel, followed by 64 QAM demodulator block. And again, the output of this is given to error rate calculation block, followed by the display block, and again to output BR to workspace. By running this both the simulation and code, I'll be showing the final output in command window. So we can see the result in command window where the simulation is being run of QPSK model, and now the running of 64 QAM simulation is being done. Both values are from simulating values are from 0 dB to 20 dB. So the simulation is complete here, and the figure is being plotted here. So we get the final bit error rate performance of QPSK versus 64 QAM in AWGN. Here, the plot helps us directly see which system works best at low and high SNR. So here, QPSK usually gives lower bit error rate at lower SNR, which is better for noisy channels, while 64 QAM achieves low bit error rate only at high SNR, but allows higher data rates. So we can see QPSK simulation plot is in blue, solid blue line, and 64 QAM is in solid red line. And the theoretical plots are in dotted lines here.
Going to explain second question of our assignment, that is BFSK and DPSK bit error rate comparison using Simulink and MATLAB. The main aim of this question is to design BFSK and DPSK transmitter and receiver models. It also add AWGN noise channel and it calculate bit error rate for different SNR values and finally compare which modulation works better. Now I am going to explain my DPSK model. In the DPSK model, I took Bernoulli binary generator, DPSK modulator baseband, AWGN channel, and the DPSK demodulator baseband and the error rate calculation. And to display, I added the block of display. In Bernoulli binary bit generator, this block generates a random sequence of binary bits. It's either of 0 or 1. It acts as input data for the system. Later, the input from the binary generator is given to DPSK modulator baseband. In this is the main block of the model. DPSK stands for differential phase shift keying. Here it came as the BPSK because I given the M as 2, M array number as 2. Hence it is coming as BPSK. It is the main block of the module. DPSK stand for differential phase shift keying. In DPSK, information is not stored in absolute phase of the signal but changes phase between consecutive symbol. If the input bit is 1, the phase is changed. If the input bit is 0, the phase kept as same. Because of this, DPSK do not require phase reference at the receiver. Now the output of this DPSK is given to AWGN channel. This blocks adds additive white Gaussian noise to the signal. It simulates a real world channel condition. I can even also control SNR values here. Means lower SNR means more noise, which increase the bit error rate. I can give an SNR values in this AWGN channel. I set mode for signal to noise ratio, that is EB by N naught, and I given SNR has 4. Now the output of this AWGN channel is given to DPSK demodulator baseband. This block is used to recover the original bit. It does not need any coherent reference. It just look at the difference in phase between two received symbols. For example, if phase changes, it detects 1 bit. If phase remains same, it detects bit 0. And we can so the demodulator simply compares the successive samples and the output of this given to error rate calculation. This block compares the transmitted bits and receiver bits and tell us the output. Now I am going to add one for loop. This is the main loop for the simulation and it helps in sweeping of EBN naught. It calculates the noise radiance division for the current EBN naught. For a current EBN naught for complex AWGN channel, N naught is equals to square root sigma to the power that can be even expressed as sigma square is equals to 1 by EBN naught into K. We are going to generate random source bits that are data bits is equals to rand n 0 I 1 into data length. Now we are coming into the simulation part of the DPSK. Initially we are encoding the differential output, that is encoded bit is equals to zeros 1 into data length and encoded bit of 1 is equals to data bits of 1. So we are going to take this 1 as an initial reference and we're going to have one for loop that encoded bits in the form of XOR data bits in and the encoded bits n minus 1. And we are going to map DPSK output 0 for plus 1 and 1 for minus 1. This line going to tell the mapping data symbol is equals to 2 into encoded bit minus 1. Next, we are going to add AWGN channel for complex noise. Noise is equals to sigma into rand n plus 1 I into sigma into rand n data length. For non-coherent DPSK demodulation, we are going to compare phase. And after the phase comparison, we will move to error counting. We'll count how many errors were there by comparing it into the original bits. Like errors in DPSK is equals to sum of XOR of the data bits and the decoded bits. This will tell us the what are the error bits in what are the error bits were there that is compared to original bits. Now we'll move to the other part of the code, that is non-coherent BPSK simulation. Non-coherent BFSK simulation, we are having two branches. One is initial energy accumulator. This initial energy accumulator indices bits from 0 to 1, signal in branch 1 and noise in branch 0. And it decides 1 if E1 is greater than E0, and it will count the error, that is with respect to the original bits and the decoded bits. After this, the simulation part is over, and we're gonna plot result with the help of figure. Uh, the inputs of binary bit is given to the BFSK modulator baseband. This is the main block of the BFSK model. BFSK stands for binary frequency shift key. Here, bit zeros are transmitted using frequency F0 and bit 1 transmitted using frequency F1. So instead of changing the amplitude of the phase, BFSK changes the frequency of the carrier bit. This frequency difference make BFSK more prone to noise channels. Now, the output of this BFSK channel is given to AWGN channel. These blocks adds additive white Gaussian noise to the BFSK. These blocks adds additive white Gaussian noise to the BFSK signal. AWGN channel simulates real-world noise like thermal noise, atmospheric noise, and other noise. Even in AWGN channel, we can adjust the value of SNR. Uh, Next, the output of this AWGN channel is given to BFSK demodulator. In this, if the received frequency matches the F0, then the demodulator output has zeros. If it matches to F1, the output has 1. Basically, the demodulator decides the bit by checking which frequency is having higher energy. Next, the output of this BFSK demodulator is given to error rate calculation. In this block compares the transmitted bit and the receiver bit. It calculates the number of errors, number of bit transferred, and finally the bit error rate. It helps us to understand the accuracy of BFSK at different SNR value, and this can be seen in the by connecting display module to the error rate calculation. Performance. I would like to say that DPSK performs better at low SNR condition because it relies on phase difference and remove the need of carrier recovery. But when it comes to BFSK, the more BFSK is more robust to noise channels. It compared to ASK, but worse than DPSK in terms of bit error performance. So DPSK performs better.
Let us start with the third problem, which is Gram-Schmidt orthogonalization. There are 5 steps involved in this problem. Step 1 is generating 3 linearly independent signals. Step 2 is applying the Gram-Schmidt orthogonalization. Step 3 is verifying orthogonality. Next, we plot the results and send it to Simulink workspace. In the first step, we create a t, which is time vector, from 0 to 1 second with 100 samples. We create 3 different signals, S1, S2, and S3. S1 is a sine wave, S2 is a cosine wave, and S3 is a straight line ramp signal. These 3 signals are linearly independent, meaning none of them can be made by adding or scaling the others. Step 2 is applying the Gram-Schmidt orthogonalization algorithm. First, we normalize S1 to get the first orthonormal vector, which is U1. We make S2 orthogonal to U1 by subtracting the projection on U1. Then we normalize it. Now S2 is both orthogonal and of unit length. Next, we remove the components of S3 that lie in the direction of U1 and U2. The remaining part is orthogonal. Now normalizing it, we get U3. Verifying orthogonality, the dot product between orthogonal signals must be 0. These print statements confirm that the signals are orthogonal. Next, we plot the orthonormal signals. The graph is created to show all 3 orthonormal signals. Finally, we send these variables to Simulink workspace. The Simulink blocks from workspace will now use U1, U2, U3, and T. Let us run the program and look at the output. So this is the output of the code. The red signal is U1, green is U2, and blue is U3. We can clearly see that all the 3 signals are orthonormal. Next, we get into Simulink, and this is the command window output. The dot products are 0, which means the signals are orthonormal. Now opening Simulink. This is the Simulink model. The from workspace blocks input signals. The 3 from workspace blocks import signals U1, U2, and U3 that were generated in MATLAB. Each signal is defined as a 2-column matrix T, U. These signals are linearly independent and were converted into orthonormal signals using the Gram-Schmidt procedure in MATLAB. Next, we use the mux block for combining the signals. The mux block takes the three separate input signals and combines them into a single multi-channel signal. That means the output is a three-element vector at each time instant. Next, we have a gain block, which is the transmission channel. The gain block here is set to 1, meaning it does not alter the signal. Next, we have a scope block. The scope block let us to examine the combined signal before it passes through the rest of the system. Through this, we can verify the waveform shape, amplitude, and time alignment. After this, we have a demux block for separating the signals. After transmission, the demux block separates the vector signals back into three individual channels. We finally have a final scope, which is the receiver verification scope. Let's run this and see. This is the transmitter side scope and this is the receiver side scope. We can see that both are similar. Looking into the fourth problem, we first load the text and compute probabilities. This text data takes our message, hello world. It finds unique symbols and counts the frequency of each and then computes the probability of each symbol needed for entropy and Huffman coding. Next, we compute source entropy. Entropy measures the minimum expected bits per symbol. And then we have a Huffman dictionary. MATLAB's built-in Huffman dict is used here. And then we build a safe code map. It handles different data types and ensures all codes become clean binary strings like zeros and ones. Then we compute the average code length and efficiency. The average length tells us how many bits each coded symbol uses, and efficiency tells us how close Huffman is to the theoretical minimum. Next, we encode text using Huffman codes. This block converts each character into numeric bits and creates the final Huffman encoded bit stream. Then we build the Hamming 7,4 code. There are 4 message bits, 3 parity check bits, and 7-bit code word. The generator matrix G used to encode and parity matrix H is used for decoding. Then we define the channel error probabilities. It simulates bit flip probabilities from 0 to 0.3. Then we have binary conversions for converting decimal ASCII to bits. The BER versus P loop is ASCII transmission simulation. Finally, we display the results and run the demo. Let us run the code. So the blue one shows the ASCII signal, red is Huffman, and yellow is Hamming 7,4. Looking into the Simulink model, before that we look at the command window output. We can see the symbol probabilities of each alphabet, the source entropy, Huffman average length, encoded Huffman bitstream length is 32 bits, and Hamming encoded bits length is 56 bits. We also have the average BER which has been plotted. Now, let's see the Simulink model. This is the Simulink block diagram. The model implements a digital communication system with Hamming coding over a binary symmetric channel and finally computes the bit error rate. The first block is the random integer generator, which generates random binary data, zeros and ones. This is our transmitted bit stream. The output is a stream of integers, zeros or ones, used as the input message to the channel encoder. The Hamming encoder converts the message bits into Hamming coded bits to allow error correction. The output is a longer encoded bit sequence. The binary symmetric channel simulates a noisy channel that flips bits randomly. Probability of error is P. It represents a real-world channel noise. Then, the Hamming decoder detects and corrects bit errors introduced by the BSC, which is binary symmetric coder. Then, the data type conversion is to converting it to Boolean. The decoder outputs integers, but the error rate block expects Boolean signals. This block ensures that TX bits are Boolean and RX bits are also Boolean. The error rate calculation compares the original bits and the decoded bits. It outputs BER, that is error rate, number of errors, and total bits comparison. Then we have the scope, which displays the bit by bit difference or the error rate over time. We can see how the channel affects the signals visually. Then the display shows the numeric value, which is the final BER. Running the Simulink model, This is the scope output, and the display shows the error rate, the number of errors, and the total bits compared. Here, the bit error rate is 0.029, and the number of errors are 26, and the total bits compared are 1004.
Hi sir, I am Manasa. In this video, I am going to explain linear block codes and cyclic codes with decoding. That is fifth question of assignment. Here we have to implement both 7/4 Hamming code and 7/4 cyclic code encoders in MATLAB. And we have to use Simulink to transmit encoded bits through a simple noisy channel that randomly introduces single bit errors. And next, integrate MATLAB based decoder blocks in Simulink for both codes and compare error correction effectiveness for 1000 bit frames. In this question, I have implemented 7,4 Hamming code and 7,4 cyclic code using both MATLAB and a Simulink. So first, I will explain my Simulink model block by block, and inside that, I will also show the function codes that I have used. So let us start. This is what my complete Simulink model, what I have generated. So this is a 4-bit random integer generator that produces the input message bits. So these message goes into two parallel encoding branches, that is Hamming 7/4 encode and Cyclic 7/4 encode. So both encoders output a 7-bit code word. The next code word passes through a single bit channel. This is the error channel. This block randomly flips 1 bit with 0.3 probability. After this noisy channel, data is decoded by a Hamming decoder, and same also follows to the single bit channel 1, that is followed by a cyclic 7/4 decoder. Finally both the outputs go to the error counter blocks, that compares the original message and decoded message to compute the BER. So this display box of the Hamming BER and cyclic BER shows the bit rate values for 1000 bits. Now let me explain each function block codes. Now coming to the Hamming 7/4 encode, let me double click on this. Now you can see this is the code I wrote inside the function block. Actually, I have just dumped this code inside the block. Let me explain what it does. First, it takes 4 bits message. It creates 7-bit code word. It keeps message bits in the position 3, 5, 6, 7. Parity bits are calculated for the positions 1 to 4. Each parity bit is calculated using a modulo 2 addition, that is XOR. So final output of this block is 7-bit Hamming code word. And next block, that is single bit channel. Let me explain this simple code here. It takes the 7-bit encoded data. There is 30% chance of flipping 1 bit. So it introduces noise just like real communication channel. So Hamming code word goes through this channel, through this noisy channel. So let us look into the next block, that is Hamming 7/4 decode. This code calculates the syndrome using a H matrix. So if syndrome is 0, there is no error. If syndrome is non-zero, which means that it finds which bit is wrong, flip that bit, and it recovers the original 4 bits. This block gives the corrected message bit to block, that is Hamming error counter. You see the code here. Let me explain this. This code simply compares the transmitted message bit and a received message bit. It counts how many errors happened and calculates the bit error rate. This bit error value is shown here in the display block. Let's run the Simulink block diagram and we can see the output there. And next, let me explain cyclic 7/4 encoder. So here I have used the generator polynomial, that is g of x is equals to x to the power 3 plus x plus 1. So that is 0, 1, 1. Appended 3 zeros. So I do the manual modulo 2 division. Remainder is my parity bit. So final code word is equal to the message bits and the remainder bits. This is how the cyclic code works. And next we'll move to the next block, that is single bit channel 1. Here actually the same procedure what we did for the Hamming 7/4 encode. So I will just skip this one. So next block, that is cyclic 7/4 decode. Here is the code. You can see from the first beginning. Here the same idea we have used for as we used for Hamming. So it will performs the division again and get the syndrome table. Then it identifies the wrong bit and corrects it, and that is it extracts the original 4 bits. This is the decoding process. Next block, that is cyclic error counter. Same as the Hamming error counter, it compares the transmitted and the received bits and calculates the bit error rate. I will run this model now. We can see the output. Here I am running this model. So here you can see the Hamming bit error rate and the cyclic bit error rate. See here, Hamming bit error rate is 0.039 and cyclic bit error rate is 0.08. So by seeing these values, we can say that so Hamming code performed better than this channel. Before doing the Simulink model, I have implemented this using MATLAB only and generated the graph also. Let me show that one. I will save the code and I will run it. Yeah, this is what the output graph I have obtained. See, you can see here the bit rate before decoding and bit rate after decoding. This is Hamming and this is cyclic. This blue color is bit rate before decoding and yellow color is bit rate after decoding. So this graph shows the bit rates. Bit rates before decoding was the same. It's actually 0.1428, which means that around 14% of the bit rates were wrong when passing through a noisy channel. After decoding, Hamming code reduced bit rate slightly from 0.1428 to 0.141. So cyclic code bit rate increased 0.20. So from this graph, we can clearly see that Hamming code performed better because it successfully corrected the more errors. So then coming to the second graph, that is absolute error counts. So in this second graph, we can see the actual number of bit errors out of 1000 test frames. Both Hamming and the cyclic had 1000 bit errors because we deliberately introduced one error in every frame to test error correction capability. After decoding, Hamming corrected the many errors. Remaining errors are 564. You can see clearly. In cyclic, corrected fewer errors, remaining the errors 836. This means that Hamming fixed the 436 errors, where cyclic fixed only the 164 errors. So numerically also Hamming is more effective at correcting the single bit errors compared to cyclic under this experiment. So from the MATLAB analysis, Hamming code gives the better error correction performance than the cyclic 74 code for the same noise level. These results match with theory also because Hamming code is perfect single bit error correcting code. The final conclusion, in this assignment, I have implemented both codes in MATLAB plus Simulink, transmitted through a noisy channel, decoded and calculated a bit rate and compared the performance. This completes the fifth question. Thank you so much.
Moving on to sixth program, which is convolution coding and Viterbi decoding. The code explanation is, first is simulation parameters are set up where the first code block generates a random binary data stream using data is equal to randi command. This is to stimulate information bits for transmission in a digital channel. And next is this convolution encoding is performed with a rate 1/2 encoder and constraint length 3 by command trellis poly to trellis. And the next is encoded bits are mapped to BPSK symbols and passed through an AWGN channel, which is in the loop here. AWGN channel is seen. And next is at the receiver side here, which is the Viterbi decoder, where this is applied to recover the original bits and correct errors from noise. Then this code automates BER calculation. Next is, we have ended the loop here, and the final part is plotting. So the results are shown in the plotting window. For that, we have used a semilogy function and we've used grid on. So the results finally show that convolution coding with Viterbi decoding gives lower bit rate at a given SNR and highlights any error floors where bit rate stops improving despite higher SNR. I'll show the simulation window now. Convolution Viterbi code simulation. So here, first block is random integer generator block. So this block produces random bits simulating the original information source in digital communication. Next is convolution encoder, which adds redundancy to random bits for error correction through convolution coding. So this makes the system robust against channel noise. This is given to BPSK modulation baseband block. This converts encoded bits into BPSK symbols. This is by mapping binary data to phase shifts for transmission. This output is given to AWGN channel, where this models the communication channel by adding additive white Gaussian noise to the modulated signal. Next is BPSK demodulated baseband block, which converts the signal which contains the noise back into binary bits. This is for preparing them for error correction. Next is the Viterbi decoder block. Here, this performs maximum likelihood decoding, which is correcting redundancy and reconstructing the original information. The output of this is given to error rate calculation, especially for receiver terminal of error rate calculation box, where it compares the decoded bits to original random bits and calculates bit error rate. Then this is then given to the output display, which displays the BER result, which helps evaluate our result. I will run the code and show the output in command window first. So this is the command window output which we have got. And finally, we get the bit rate performance graph. In graph, this is the bit rate performance convolution coding with Viterbi decoding. Here we can see that uncoded BPSK plot is represented by a red solid line, and convolution code, which is of rate 1/2, is represented by a blue solid line. So this graph shows that bit error rate performance versus SNR dB in dB for BPSK modulation. So as SNR increases, the bit error rate decreases gradually for uncoded BPSK, and this blue line shows bit error rate with convolution coding and Viterbi decoding. So here the bit error rate drops much faster as SNR increases and reaches lower error rates earlier than the uncoded case. So convolution coding with Viterbi decoding significantly improves bit error rate, which is error performance, at all SNR values compared to uncoded BPSK. So the system can transmit data much more reliably in noisy conditions. Thank you.